Physics, Day 140, Electric Current. And the goal here is to understand electric current in the context of this basic electric circuit. Hopefully you've already finished Circuit Lab 1, where we lit up the light bulb with the basic battery or two batteries. Doesn't matter how many batteries, but I have a picture of this down here below. Something similar to what you did in the lab, either in the virtual lab or in the real lab with real wires and real batteries. So the definition of electric current is the flow of electric charge. And one thing before I get going too far here, it's very similar to current in a river. Current in a river is invoking the flow of water. How much water is flowing, how fast the water is flowing in a sense. And that's what it is for electric current as well. It's the flow or movement of charge in the wires, and it's the electrons that are moving in the wires. The wires are full of protons and electrons. And what happens in the circuit, there's a battery. Well, let me go back up here. Current is caused by an electric potential difference, delta V, which is the battery. Most batteries that you get in a store, like AA, AAA, believe it or not, they're all 1.5 volts. Just the bigger ones last longer. They have more energy stored. But a volt is the amount of energy per coulomb of charge that it can push, so to speak. We'll talk more about that. Well, right here, the voltage can be thought of as the pressure or push that pushes the electrons. So what you found out in the lab, and as you're looking at these pictures, first of all, you have to have a complete circuit. And that's one of the bugaboos sometimes when you're actually using real wires and real batteries, is sometimes you don't have a good connection. You have to have a lot of good solid connections where metal is touching metal. Like, for example, in this particular situation down here in these pictures, these pictorial diagrams over here down on the left, there's a gap right here. There's a gap right there. There'll be no circuit. It's called an open circuit, and no current will flow. This second diagram is what you hopefully successfully did in the lab when you touch a wire to one end of the battery and then to the bottom of the bulb, because the bottom of the bulb, believe it or not, there is a thin wire connected to the bottom of this bulb. Let me draw this. There's a thin wire from the bottom of the bulb, and I can get this lined up. I have to backtrack that a little bit. And then it goes up through this filament here, and then back down to the side and around through this wire. Let me just complete this path. So it's a looping path. Hopefully I get that connected. That's pretty good there. In that diagram I just drew, all right, I'll use this pen now. This is the completed circuit. And the wires, the battery, the light bulb is full of electrons and protons. But once again, the electrons are the things that move in the wires. They rotate, kind of like musical chairs, so to speak. So when the music starts playing, in other words, when you connect the circuit, everything starts to rotate like musical chairs. Except for in musical chairs, you start taking out chairs, and there's not enough space for everybody. But there's a space for everybody here. If there's 5,000 electrons, there's 5,000 chairs, so to speak, 5,000 protons. There's way more than that. It's millions and billions of electrons. But basically, once you connect the circuit, they all start rotating. The electrons that are here start moving up this way. Actually, technically, this is the negative side of this battery. I think it's labeled, yeah. The electrons actually start here and they start going this way. The electrons go from the negative and they go through this wire, and there's electrons everywhere, pushing on each other basically and rotating just like in musical chairs. When they go through this filament, there's a lot of friction here, and it causes heat and light. This filament is usually tungsten. So now the arrows here, and I'll make note of this later on, give you the direction of what's called conventional flow. It's a little confusing, but this is kind of what was determined before we really figured out that it was the electrons that were moving in the wires. They kind of thought, or just kind of supposed, that the positive particles were moving. Doesn't really matter, in a sense, for us, for now, which way we're going. We know that there's a flow. There's movement in these wires. The electrons always go from negative to positive, this way around. But if they were protons, they'd be going the other way around. So a positive moving in one direction is the same as a negative going the other direction. You don't need to worry about that a whole lot right now. But you have to have a complete circuit. Now, this diagram here is not preferred as far as a diagram to be drawn all the time, because it's too there's too much to draw there. So we have what are called schematic diagrams here in the middle. So this is the way it's commonly drawn if you're an electrical engineer, which you may or may not be someday, but you need to understand these for now, and these aren't that bad. This is a basic diagram that tells you that this represents this battery over here. In this case, it might be a 1.5 volt battery, but somebody's saying, okay, this is a 10 volt battery. It's a long, a short, a long, a short. Sometimes you do another long, another short. Sometimes just a single pair of long and short. But this black line here represents a wire, and we draw them nice and square here, but in real life they're usually, curved, like over in this diagram here. Nothing's really square about it. The wires kind of curve and bend. But this is a kind of nice, neat way to draw it. This, and we'll talk more about that tomorrow, is called a resistor. In this case, it represents this light bulb. It's basically the friction caused as the electrons try to go through that light bulb. There's friction that it's kind of like rubbing your hands together. They get hot, and they get hot enough here to give off heat and light. And you're going to learn again tomorrow. Today it's not as important, but resistance, the friction in electrical circuits, is measured in what's called ohms, and here's the symbol for ohms. It's a 5 ohm resistor in this case. We'll come back to that tomorrow. And then this is another wire. So there would be 2 wires here. There's the battery, is a wire that connects here to here, which is maybe to the bottom of that bulb over here on the left, and then the other wire that's down here. All right, so there's a water analogy. And the water analogy is kind of like this. The pump that pumps water through pipes is analogous to the battery, or the battery is analogous to the pump. So in this diagram, the battery is like the pump would be in a water system. In a water system, we have pipes that the water flows through. In this case, you have wires that the electrons flow through or move through. And it's kind of like musical chairs, like rotating around. And then you have, in pipes, you get clogs or restrictions that cause friction or slowdowns. Those are like, in this case, the resistors, in this case, the light bulb. I'm going to call them in generic form a resistor. We'll talk more about that tomorrow. Okay, in this case, it's the light bulb is the resistor that slows down the electrons. They go really fast through wires. They're kind of like superhighways. They have virtually zero resistance. It's very easy for electrons to travel through wires, which is what we want. But when they go to a resistor, through a resistor, it does some kind of functional thing. In this case, creates so much friction it gives off light, which is what we want this particular circuit to do. All right, so as I mentioned before, the electrons, where do the flowing electrons come from? Well, they're everywhere. They come from the wires and other circuit elements. All right, the light bulb has electrons. I mean, the tungsten filament is the element tungsten, which I forget which element it is on the periodic table, but I don't know. I'm going to make up a number that's probably not right. It's element number 72. It has 72 protons in a nucleus and then 72 electrons, but some of the outer electrons are the ones that move through the filament. Then the wires are copper, and those have, once again, copper is, I'm just making up a number. I wish I had it handy, but you could look it up. Copper is element number 55. There's a bunch of electrons, and the outer electrons are loose, and they start moving. But everything rotates around. The wires are full of electrons that are stationary when there's no pushing them, but when the battery starts pushing on one electron, they all start pushing on each other, and they move around like musical chairs, like I mentioned before. So the battery is not the source of the electrons, it's the source of the push for the electrons. The battery pushes the electrons. As I mentioned before in that diagram at the top, the conventional direction, when we draw arrows to show the flow, is that the flow of charge is from positive to negative. I'll come back to that. It really isn't that important for problem solving, but make a note, as I said before, the electrons are actually going in the other direction. They go from negative to positive. We'll come back to that, but that's the conventional. So I'll make note of that and put that in the back of your mind. We'll come back to that. So now the mathematical definition of electric current, down here on the left. Current is the charge flow per unit of time, and the symbols are I. I stands for current, equals charge flow, which is Q. Sometimes they say delta Q over delta T. I usually leave the delta off. I can put it in now, actually. You can leave it off. Delta Q over delta T, we usually do. We usually leave that off. But to be technical, it's how much charge flows past a given point in a given time. If this were a water pipe system, it'd be like gallons per minute. That's the analogy. But here, it's the number of coulombs per second. It's a charge. You could say how many electrons per second. We're not going to figure that out right now, but you could divide the total charge by the charge on the electron to figure that out like we did in the previous section. But number of coulombs per second passing a given point. Once again, in a water system, it could be like 5 gallons per minute. Here it might be 3 coulombs per second. Very similar idea. So here, and then the units then, it's coulombs per second, but we have a name for a coulomb per second. A coulomb per second is called an ampere, or sometimes it's called an amp, symbolized with A. You've probably heard of that before. So a lot of times we call it, like I said, we say amp instead of ampere, named after a famous French physicist. All right, but here's a couple of problems. If 27 coulombs of charge pass a fixed location in 2 minutes, what is the current? Well, so we have the equation I equals Q over T, and the charge is 27 coulombs, so the current is 27 coulombs. That's the proper units, but we need time in seconds. 2 minutes is 120 seconds, so you got to either remember that. Each minute is 60 seconds. So we have 27 coulombs in 120 seconds, and that comes out to be, well, 0.225. I'm going to round up to 2 sig figs. 0.23 coulombs per second, but a coulomb per second is called an amp. I'll write it out this time, but sometimes you can just put an A there for that. And that's the flow everywhere. That's the amount of coulombs per second flowing everywhere in the system. There's that much charge at any spot in the system, because once again, it's like musical chairs. Everything is moving all at once. All right, so kind of a reverse problem. If the current is 3 amps, how many electrons pass the fixed point in 10 minutes? So I'm just going to plug in once again. I have now the I value is 3 equals Q over T. Well, 10 minutes is 600 seconds. All right, so if I solve for Q here, Q comes out to be, well, 3 times 6 is 18, so it's 1,800 coulombs of charge. But the problem says how many electrons. So how many electrons is that? So once again, it doesn't matter where you are in the circuit, that many coulombs of charge is passing by that spot. Like if you were if you were in a pipe, this is asking for how many gallons go past, how many gallons per second. This is coulombs per second. How many electrons would you see go past you if you were, like, say you were standing, by the light bulb or inside the light bulb? How many electrons? That's a lot of electrons. Basically, you take, like we did last chapter, you take that large number and divide by the charge of 1 electron, which is 1.60 times 10 to the negative 19th, which I don't expect you to memorize. And that tells you how many electrons. And at 2 sig figs, that's 1.1 times 10 to the 22nd electrons. That's just a number. You really don't have to put units here, but I'll put 1.1 times 10 to the 22nd electrons. Squeezing this in. And I'll circle that answer. Let's try a different color. That's the answer to this part of the problem. That many electrons are passing any given point in that circuit at any given time. Okay, and finally here, a couple of different types of circuits. You have what are called DC circuits, direct current circuits, where the current flows only in one direction. Basically, any circuit with a battery, which is the ones that we've been doing, any circuit with a battery. And you have alternating current circuits, where the current changes. It goes forward and backwards and forwards and backwards. And those kind of circuits, the electrons end up going nowhere. They just get pushed forward, then backwards, and forward and backwards. The current just keeps changing directions, and there's a reason like that's beneficial, and we'll talk more about that later. In the United States, it's anything with an outlet. Anything with an outlet, we plug things into the wall. Any electronic device. Well, other than battery chargers, like in your phones, those are all batteries. Those are direct current in your phones, iPad. But in outlets, anything that plugs into an outlet, that's alternating current. In the United States of America, the outlets are 60 hertz, in other countries, the frequency of alternation is different. You can see it for China and Korea. It's different, possibly different voltages. That's why you need adapters to plug in the chargers, which are transformer. We'll talk about those later on, to change it to the correct voltage and current for your particular device when you're in another country. Interestingly enough, if you put these words together, AC/DC, you might invoke a famous band from back in the, I guess, 70s, and I think that's a spin-off from this particular concept, AC/DC, alternating current, direct current. Anything that we do in this class is going to be with direct currents, with batteries, 1.5 volt batteries, or a couple of 1.5 volt batteries together that gives you 3 volts, or even maybe 4.5 or 6 volts. Everything we're going to do is safe. Of course, when you're doing it as a virtual lab, it's perfectly safe. There's just your screen. One final thing here, diodes. We're not going to do a whole lot with diodes, but I want to mention them because they have come up before in this class this year. And the ones on the left over here you really haven't seen. These are kind of like one-way connectors in a circuit. When you put these in a circuit, and for direct current circuits, they don't really matter because the current doesn't go forward and backwards, But diodes are like one-way streets. If you connect them in a particular circuit, they don't let the current, so to speak, go backwards. It only lets it go forward. These are the most common LEDs. You've heard that term before when we did the cell phone lab, light-emitting diodes. And now we have light bulbs that are very efficient at giving off light. They give off very little heat, and we like to use those types of light bulbs nowadays, LED lights, because they are green, so to speak. They save a lot of energy, but they let current only go in one direction. They don't let the current back up. We'll talk more about those later on. So current is the flow of charge. It's usually electrons, like 99.99% of the time it's electrons, moving through a wire, kind of like in the form of musical chairs.